I will discuss the so I will mainly discuss the cubic wave equation and with radial data. So what? Yeah. Yeah. Okay. Oh yeah, yeah. Okay. Yes. So this is. Yeah, there we go. So mu is equal to plus or minus 1, and that means that we could either have a focusing or a defocusing problem. Now, yeah, so let me write it down first. Yeah, so the this problem is, I will discuss it in dimensions 3 and 5. And the reason is because dimensions 4 has already been done. Dimensions 4 will be is the energy critical case. And what that means is if you have a solution you have a family of solutions and given by this parameter lambda, where lambda is greater than 0. And so in the dimension d equals 4, then this is going to be H1 invariant. And we see here from this conserved quantity energy that you have the H1 norm conserved. So that case has already been dealt with. In 3 dimensions, you have the H to the 1/2 critical case. And that has been, that's something that Andrew Lowry and I worked on, and we put the paper on the archive maybe in April, I think. And then we have the D equals 5 case, and that's something that Einar Bulut has dealt with in the defocusing case, which is mu equals 1, but not in the focusing case. And the reason why we can now use do the focusing case is because we have this method called the channels of energy method. That's, I don't know, maybe I don't want to, I think it's a pretty recent method that allows us to deal with focusing equations, because you don't have a Morowitz estimate that you would have in that's available to you in the defocusing case. So let me just go ahead and quickly describe the work that's been done already, just so that I don't forget to do that. Okay, so there we go. So we're using the concentration compactness method, which is a fairly commonly used method. And it was used by Bahuri and Girard in various things, and also Bourgain used this with the NLS. Gerlachus and Struve, prior to that, did the 3D energy critical problem with mu equals +1, and then Koenig and Merrill used the concentration compactness method to deal with the 4D energy critical problem. Kilp and Vishon, the 3D supercritical problem. So that would be, so SC is the critical exponent, so if you had SC greater than 1. And then Boulud has dealt with the supercritical for defocus, so supercritical. So the defocusing 5D, and then D greater than or equal to 6. And then we have a student of Koenig, Rupeng Shen, who dealt with D equals 3 for 1/2 between the critical S between 1/2 and 1. So we're dealing with D equals 3, S of C equals 1/2, and D equals 5, S of C equals 3/2. So it's supercritical. Yeah. So and because we don't have a conserved quantity, we assume that we have a upper bound on our norm. So So, in other words, we have if we have an upper bound for all time on the critical norm, then we have covariance and scattering, and this is equivalent, as was seen in Monica's talk on Monday, to the scattering size being finite. So, so I'll just write it as where in D equals 3, S of I and D equals 5. And a brief check would show that these are also scale invariant quantities. So I suppose the first thing to say is, why do we care about such a thing? I mean, okay, so you assumed something to be true. Great. Why is that? Why care? And I've gone myself. I'll admit I've gone back and forth on this issue of whether it's relevant or not to assume, a bound. But in this case, I suppose I've come to the conclusion that it is, probably because I did this paper. But there's two issues that need to be pointed out with this, or perhaps more than two. That you have this in the defocusing case, or in the focusing case rather, you have an ODE, which you can use, which is going to blow up in finite time. And so you can use this ODE, along with find a propagation speed to construct a blow-up solution in the focusing case. But the critical norm blows up, along with that. So we know that. So what we're ruling out here is what's called type 2 blow-up, which is where the critical norm stays bounded, but you still have blow-up in scattering size. And there's been a number of work, including very recently, maybe a week ago, there was a paper showing that type 2 blow-up does occur sometimes. So we have a result of Krieger and Schlag and Tataru for the wave equation showing a focusing type 2 blow-up. And then recently, Merrill and Raphael and Rodiansky showed type 2 blow-up for a D greater than or equal to 11 and an energy supercritical for the NLS. So, yeah, for the NLS. So it's not such a obvious thing that you never have type 2 blow-up. And we're just in the process of gradually proving all these different theorems for all the possible cases that might arise. Yeah. So, and Merrill and Zog proved that if you have a blow-up of the critical norms, I believe it was for D equals 3, then the blow-up has to be in a self-similar way, that you can't just have any old blow-up of the h1/2 norm that you like. And so that perhaps that could be used to somehow then show that the h1, somehow rule out the h1/2 norm blowing up, because it has to blow up in a specific way. So that would be an interesting problem, I think. Oh, okay. So at this point, I will describe the concentration compactness method in a bit of brief explanation. And I realized last night when I was writing this that I had to give you a literature lesson, perhaps. So you know the quote, "Ah, what a tangled web we weave when first we practice to deceive." Most people think that's Shakespeare. It's not. It was Sir Walter Scott who said that. So anyway, but that's the applicable thing for the concentration compactness method, right? Like that's how the method works. I mean, it really is. So you know that you have global well-posedness and scattering for small data, and Monica talked about this. And then you also know you have some kind of perturbation theory. So you know if you have a small perturbation of a solution that scatters, then you're going to have scattering. And so then therefore you know there has to be a minimal energy or mass or what have you solution that blows up, if it ever blows up. So then you say, okay, well, what if I have such a solution? And if you have such a solution, and Mike Christ mentioned this in his talk yesterday, he basically said you have to have everybody working together, right? So like yesterday when we played soccer and there was even teams that could just stand around and do nothing. But usually when there's even teams, you have to have someone. And it's the same idea as in this problem. You have to have all your solutions working together. They can't be somehow divided and off doing their own thing. And therefore, of course, then they have to be in a single wave packet is what it boils down to. And this is by now a pretty standard argument. And so we have the upshot of all this. Is that this lies in a precompact set. Now, again, Chris talked about how you can't really say it lies in a compact set because you have all these groups that act on your solution. But because it's radial, we have a bit of improvement because we know it has to stay centered at the origin. So all you have to take into account is this scaling parameter. And so then we have this solution now that has to live in this precompact set for all time. But actually, that's not quite true, because we actually have a bunch of solutions that have to lie in a precompact set for all time, because you can always shift your time to give you a new initial data of a solution, right? So you in fact get this whole family of solutions. And because they're precompact, you can take a limit of solutions that and get a very special solution. And so then usually the argument then becomes you kind of find 2 or 3 special solutions that you rule out. So and then you show those solutions don't exist, and therefore then the blow-up solution is caught in its own web of lies that it's created, and it well, I mean, this is exactly what we're doing, and it took, and in fact, I will just emphasize, because it was something that I had to think about for a while, is that when you're showing that you eventually obtain these 2 or 3 enemies, and I remember thinking, well, that's not true. I can think of a lot of other minimal mass blow-up solutions other than that, and that's true. But we're dealing with the 2 or 3 enemies that are going to crack first, and then once they crack, they're going to basically rat everybody else out, and the whole operation falls apart. That's really how it is basically what we're doing. So then let me say what our enemies are. So d equals 3. We have this scenario that we have to deal with. And when d equals 5, we have so these are in one case 1 scenario, in one case 2 scenarios that you have to deal with. So at this point now we're at the position where we want to show that such a solution of these forms doesn't exist, and then we have global outposedness and scatter. So what we want to do to show that these solutions don't exist is we want to make use of our conserved quantities and our Morowitz estimates. At some point, we have to do some nonlinear type of estimate on the solution and show we get a contradiction. So we want to show that so I'll just create. So, in other words, that's the only solution that can be lie in a compact set for all time is u equals 0. We know, of course, that does, right, because it's constant. But so then we need to make use of some tools in order to rule this solution out. And so one tool that proved very effective was the double duhamel trick. That's not really a thing. And, oh, yeah. So if we look on, so you, do what? Ah, thank you. Yes, that's right. That's right. Thank you very much. That's right. That's right. Yeah, that's right. Yeah, that's right. So we obtain these two gains in regularity. So in this case, we're right, because remember in d equals 3, it's h1 half critical, and d equals 5, it's h3 halves critical. So we gain an extra half derivative. No, it's no, because as n of t goes to 0, that means our solution gets more and more spread out, right? Because we have to, if n of t goes to 0, we have to, we have to pull it back together to get it to be in the compact set. So that means it's very spread out. Yeah. Yeah. Because we're going up. See, because this is H2 here. Yeah. Yeah. And so, yeah, so the point is we use the double duhamel trick to gain a half of a derivative. In fact, you can gain a whole derivative here. But then it would, yeah, so I might as well. Right. Yeah, so if you look on this compact set here, you see that's exactly what you would, that's the most that you could, that's the best, that's within a constant of the optimal improvement. Because your solution, because of your scaling, your solution has to lie in a compact set. And so then this is optimal improvement. And so this was actually the beginning of our collaboration, because I was giving a talk in the student seminar on the double duhamel trick, and this is so maybe I'll write down the people who have been involved in this. And so we have these 3 papers here on the NLS mass critical, using the in and out decomposition. But I think you can also do the same argument with the double duhamel trick. So anyway, so I'll write it like that. And then you have this paper for the energy critical. And then Blowup and Kilp and Vishon and Shen for the wave. And then Tau. And myself for the KdV equation. So this is a method for called the double duhamel trick, which has proved to be quite useful in a number of papers. And so I presented this in the student seminar at UC Berkeley of this method you can use to solve all these problems. And I mainly concentrated on the KdV and then also the energy critical problem, where they show that you can get L2 regularity. Because you have H1, you show you get L2. And so Andrew Lowry said to me, well, does this method work to go to higher regularity as well? I said, yeah, I mean, there's this 3 papers here that you can use to get up to H1. And he said, well, we should talk about this. And so he said, like, can you get to H2 with a wave equation? And I said, well, if it's radial, probably. And so we talked about it. So that's the I don't know, the advice I guess I have for you is give talks in the student seminar, because you can help people learn, and you also get something out of it yourself probably too. So yeah. So. Oh, okay. Oh, thank you. Yeah, sure. Yeah, so I'll write it over here. Thank you. Yeah, so the idea of that is as follows for the wave equation. So we let V u sub t, and we want to show that this lies in our space, whatever that might be, and so we take a inner product, and we know that V of t equals okay, so hey, look, I'm sure I messed up a sign or something somewhere. I think there's but importantly, there's this. Yeah. So I'm sure I messed up a sign here somewhere in there. And so then so if you're wanting to calculate this inner product at t naught, or at t rather, then you can choose your t naught wherever you want, and so you choose t naught greater than t in one direction and less than t in the other, and then you integrate that. And what's nice is as you take this should be t minus t naught. As you take t naught heading off to the inf or the sup of your interval, then this term is, because v of t naught is compact in a compact set, then it's going to converge weakly to 0 in your critical norm. In your critical norm. Now you can use, you have to use some Fourier truncation or actually we prefer to use a integrating with a C0 infinity function that approached the delta function, because we didn't want to lose our finite propagation speed. So instead of taking a Fourier truncation, we just modified it slightly to deal with that, and we don't want to lose because the finite propagation speed comes up in a very clear way, because so you have these terms go to 0 weakly, and so therefore you're left with just these terms in your inner product. But now look, you have an extra derivative that you've gained. So so that's where you can jump from say 3/2 to 5/2, for example. And so you're left with this integral. Okay, and then you're just left with calculating this inner product, and at that point you have to do a little linear algebra. And say, well, if and that's just a general fact, and then we want to choose our A's and B's appropriately. So we choose our A's that gives us a good Strickhart's type norm, and then our B's that gives us that when an inner product happens, then you get a good bound. So so the B's we use the Sharp-Huygens principle. So we and so we take the interior light cone C times T and then okay, let's say we're working at 0. Okay, we're calculating the inner product at 0. So T is greater than and not. So we have this. We're integrating these parts, and well, but by the Sharp-Huygens principle, so you can always take this inner product. This is bad. I'm gonna change my. So this is a Sharp-Huygens principle then, because tau minus tau prime minus tau is going to take all of this stuff in this inner light cone, let's say, C is a fourth or something, and put it out here, right? It puts it out here, so that inner product is actually going to be 0. Now, I'm glossing over some things, because if you have taking a half derivative or whatever, it's a non-local operator. But the point is that, but this kind of heuristic still works if you take your frequencies truncations carefully and things like that. You can do it. But a point remains that you can do the same trick for the NLS too, where you don't have Sharp-Huygens principle, right? So you don't necessarily need Sharp-Huygens principle, although it's certainly nice to say something 0, right? It goes away then. So then you're left with the rest. And the rest you can use the radial Sobolev embedding. So U cubed for x so in radial data, we have so you have this radial embedding in any dimension. So no, you don't have it in 3 dimensions, but you can there's ways to work around it. So, you don't need all of it, is the point, because you're showing then that this SC is bounded by U 1 over T squared, right? Because the SC norm, the critical norm is bounded, and so then when you integrate this so when you're taking just the Strickhart's norm, then this is bounded by n of t, n of tau, which gives you a full gain of regularity, right? Because it gains a full derivative because you had the 1 over square root of minus Laplacian in front. So you picked up the derivative from there. So you gain a full derivative with the n of t when you have in 5 dimensions. In 3 dimensions, you can't quite do that because you don't quite have this embedding here in 3 dimensions because it fails. But so you can work around it though, and as long as you're content to not go all the way up to 3 halves, but you really don't need to go all the way to 3 halves. So you can gain this regularity here, and then once you've done that, then you write that in for A, right? Because that gives you the extra, and then you just have left the short intervals, which you can sort of bootstrap your way to victory with that. So at that point, then you're pretty much done with the 3-dimensional case. So, oops. There we go. Yeah. So, so if you have 3D, you have either n of t goes to 0, in which case you have to have the energy identically 0. And then there's a result of Killip and Vishon and Stovall, which says that if your energy is less than or equal to 0, you have to either blow up in both time directions or you have u identically 0. And of course, I mean, the scenario D, the scenario I talked about was you had n of t less than or equal to 1 on 0 to infinity, so you're stuck with u identically 0. If the case of n of t equals to or equals is similar to 1, then you use Morowitz. You have a Morowitz estimate that you can use that actually works in the focusing case as well. So I can tell you more about that if you want. So then what about d equals 5? Well, in this case, you also have to use a double duhamel trick again, because you not only want to go up to H2, you also want to go down to H1. Or you want to show that your solution. So if you have n of t greater than or equal to 1, you can show that so in this case we have we go below H1, so that all that does is show that U is compact in H1 for all time. And then we can use the channels of energy argument of Duykertz and Koenig and Merrill, which says that if you have something that's compact in H1, then you know that outside of some ball R, then you have to have small energy, and we actually have we can use our radial sublevel embedding again to show that the small energy stuff out here has to escape to, has to more or less be dominated by the free solution, and taking advantage of the fact that it's radial means that that the only way for that to happen is for this to be equal to a soliton for your wave equation. But then you can keep making that argument and show, in fact, it has to be a soliton on the whole r to the 5. But if it's a soliton for the whole r to 5, then it's not in h to 3 halves, because the soliton is not in h to 3 halves. So you have a contradiction. In the case of the self-similar solution, you use another argument of Deukert's, Koenig, and Merrill, which is to say, so in this case you have again, using Mike Chris, sort of heuristic of, well, everybody has to work together for a blow-up solution. If you have a solution that blows up in finite time, it must live inside this light cone. And so then you can rescale that, take W equal e to the minus s times u times r. And then in that case, then you've turned it into a solution that lives in a cylinder. And then you can show you have a monotone quantity, which means you have to have this has to converge to a stationary solution. So then you're just left with solving an elliptic PDE. The elliptic PDE was a little bit more difficult because in the H3 halves case, critical case, then it was for if you have a P higher than 3, I think. So I had to use. So actually, that was an interesting argument because it took me maybe an afternoon to solve this. At the end of the day, then you show the solution to your elliptic PDE is 0. And we take advantage of the fact that the solution lies in H2. So we use that extra regularity in this case for the elliptic problem. And it was one of those things where, because I taught PDEs in the fall, and after I proved it, I realized I had proved it already, in a general setting from something in Taylor's book. And I remembered exactly where I was when I proved it because it was on Halloween night. And so I proved it while watching Children of the Corn. So I don't know, maybe that's why I didn't remember it, I don't know. But, okay, which I recommend the Halloween movie over Children of the Corn, but the original, not the 2007 version. So anyway, that's my other literary suggestion to you. Yeah. So lastly, I will talk about one application of our 5D method, and that is to wave maps. So if we have a one equivariant wave map, and there are a lot of people in the audience who know a lot more about wave maps than I do, but I will simply, so if we have a one equivariant wave map that maps into, with a target, either S3 or H3, then if U is equal to psi over R, U sub tt. So this is a map from R3, a three-dimensional wave map. But when you take U is equal to psi over R, then you pick up a 4 over R, right? So you put it in 5D. So, or it turns into a 5D type problem. A phi? Okay.
So you take TR theta phi,
Uh-huh.
and it goes to C theta phi.
Yeah. Okay, thank you. Thank you. Yeah. Okay, so we have this problem, and this is both a defocusing or focusing problem, depending. So this is the defocusing, this is the focusing. But now let's look at this Taylor expansion here. So we have I think that's the right Taylor expansion. You what? Okay. The point of it is that you get cancellation. Oh, you get cancellation in the what? Oh, yeah, right. There we go. So, and is this 2k plus 1 too? Yeah. Okay, great. So the point is that you get cancellation. You get cancellation in the first one, right? And then the third one, you pick up a 8u cubed, and then you've got more terms beyond that. Now, remember we know that in 5D, we're in 5D now, that u h dot to the 3 halves. So we know that. So all these other terms, they might be big, but they're bounded, right? And so we can go ahead and just sum this up term by term, right? But this term here, we treat it just like a cubic problem, and then the other terms we're going to have r squared, u to the 5th, and so on and so forth. And we can use all those same tools that we have for those problems. We just have to we're just going to have something a bound that's going to depend on this norm here, right? And of course, if you replace this with a sinh, you do something here with the sign. I don't remember what, but you do something. Probably take it. I don't know. Take it away maybe. And so then you get the same thing. You get the exact same thing because all you're ever doing is just brutally analyzing it term by term, and all those same techniques apply. So then you still get the solution has to be in a more regular space, so you can again use the channels of energy argument and the elliptic PDE type argument and so on and so forth to rule out the self-similar case. So that's about just enough time. So thank you for your attention. Yeah. Okay. Yeah. So that actually, it was nice that this happened, but yeah, everything worked out nicely. But if you take your Morowitz estimate, d by dt of u so you have your standard, the what? Yeah, it gives the energy. And now you have to truncate in space, of course, but that's very easy. That's okay because you know that it's the point is you can go. The point is because you go, not only do you go up to h1, but you can get up a little bit above h1 as long as you don't go all the way to h to the 3 halves. So you can show in the case of entity identically 1 that your solution has to be compact in h1, not just modulo scaling. There is no scaling; it's just compact. So then you take you truncate in space, and that truncation is not going to change your energy too much. You know, it's going to be pretty close to the energy. And you can get these upper bounds on this. You know, you can show that the upper limits of these is bounded by some little o of t, where t is the size of your interval, right? And so then you're saying that the integral from 0 to t of this is bounded by little o of t. So then the average of your energy goes to 0. Well, energy is conserved, so then energy has to be 0 in that case. And we know that if energy is 0 and you have a solution that's global in one time direction, it must be u equals 0. Yeah. So that was really nice that, you know, in 3 dimensions that worked out. Because we actually tried to do channels of energy and we couldn't get it, and then we thought, well, maybe oh, great. Yeah. So. Well, I'm pretty partial to 3 dimensions myself, so.